Tonight we welcome Dr. Alfredo Carpineti, who's an astrophysicist and science communicator. He was born on a sunny Mardi Gras in the town of Anzio, which is also the birthplace of Nero and Caligula. He is a senior staff writer and space correspondent for IFL Science, currently writing his debut book called Invisible Rainbows. He is the chair and founder of Pride in STEM, an award-nominated British charity dedicated to supporting and showcasing LGBTQ+ people in science, technology, engineering and maths. So let's give a big welcome to Dr. Alfredo Carpineti.
Hello everyone. Thank you so much for having me. It is such a pleasure to be with you, even though we are just together virtually. Let me share my screen and my slides. You should be able to see them now. And until somebody stops me and say we cannot see anything, I will continue and pretend that we are.
Can't see it, don't panic.
You can?
Yes.
Perfect. Okay, you heard everything already about me. I'm an astrophysicist. I work as a journalist for IFL Science, also science communicator, activist, and as mentioned, I have been writing a book. Well, the book is written, the manuscript has been submitted. I'm just waiting for the date that they're going to communicate me that the book is going to be out, probably early next year. So for you tonight, I have something that I'm calling a tasting menu of a talk, mostly because there is so much to talk about when we discuss light beyond the visible spectrum, and in particular how we use that light to understand the universe. Since the 1800s, since we have worked out as humans that there is light beyond the visible, we've been using it to try and understand the cosmos. And almost from the very beginning, we started realizing that there was a lot more in the universe that's what we could sense. And this is something that has always fascinated me, that we have this ability to develop technology that help us go beyond our senses and to discover so many phenomena that we didn't know existed, but also to understand objects that and celestial bodies that we knew fairly well in a completely new light, pardon the pun. So to cover in a short talk all those amazing discoveries, it's a lot. Every single wavelength could easily have their own talks. Every discovery that I'm going to discuss can have their own talk. So is just a tasting menu. You're gonna have a lot of antipasti, lots of tapas for you to try on the different wavelengths. And what I say is you do not have to memorize anything. There's gonna be a lot of fun facts, a lot of brilliant things, but you don't have to like, oh, I need to remember everything. No exam at the end. The only thing that I want you to do is enjoy this ride and just think of how incredible that human ingenuity allowed us to make all these discoveries. Like, we are supposed to be apes scavenging in the savannah after lions, and we're here discussing the deepest mystery of the universe, and that is amazing. So my book and the talk is called Invisible Rainbows, and because it's this idea of invisible rainbow that started me on this journey. I was making cocktails at Norwich Science Festival 4 years ago, and I and was making a cocktails with rainbows because those are always fun. And I was explaining astronomy at the same time, and you will see shortly where the overlap between cocktails and astronomy comes from. And somebody asked, are there rainbows on our planet? And the first assumption was like, there must be. Like, there's nothing about Earth that should be unique. Like, we know that we haven't found life elsewhere, but we also need to assume that life cannot be a prerogative of Earth. We don't know enough about life and planets to see that Earth is absolutely unique and special. So we need to assume that there might be somewhere else. And my first thought was like, well, there's only one other world in the solar system where there is rain, and that is Titan. And I was like, could there be rainbows there? And at first I thought, oh, probably not. The atmosphere of Titan, as you can see there, it's very, very opaque. Titan is a big orange ball. But that, when I went and then look up the atmosphere, that was just in invisible light. That's what Titan would look like to us if we were on a spacecraft going around. But if you could see in infrared, things are very different. That's Titan in infrared. And if you see, there is this little area in the middle of those clouds that is a lake. And the bright spot, that is sunlight reflecting on a lake. And it's incredible. It's we are seeing sunlight reflecting on a lake, and it's not a lake of water. It's a lake of hydrocarbons, mostly methane, because Thailand is extremely cold. And the rain too is not water rain, is a rain of methane, which is transparent to sunlight, just like water, and it works just like water. It could create rainbows. We never seen rainbows on Titan, not yet. Maybe when NASA send the Dragonfly mission, we'll be able to capture a Titan rainbow. I don't know if they equipped it with an infrared camera, but I hope they did. They will do. But this is there are rainbows in the rest of the universe, but sometimes they are invisible to us. So the point is that there is a lot of light that we cannot see. And we're going to go from the longest wavelength, which is radio waves, to the shortest, that is gamma rays. And we're going to discuss some of the very incredible ways that we use the different wavelengths to study the universe. So let's start with radio waves. And with absolutely my favorite radio wave picture. These are the first images of supermassive black holes. One is M87 star, which is at the center of the massive elliptical galaxy M87, and it is about 6 billion times the mass of our sun. One single object, 6 billion times the mass of our sun. Incredible. And next to it is Sagittarius A star, which is the friendly neighborhood supermassive black hole at the center of the Milky Way, which is a lot smaller, 4.6 million times the mass of our sun. So a little bit smaller and a lot more quiet, as no jets, is a very chill black hole. And radio waves are important because for the first time we were able to see the wavelength, the light that is twisted around the black hole, immense gravity. And we wouldn't be able to do it with any other wavelength because there is a special property that is shared among the wavelength of light, but is particularly useful in radio waves. If you have two radio telescopes with a certain distance from each other, let's say 10 kilometers, if you take the measurement of the same object at the same time, it's like you can combine the images in a way that is like you have a radio telescope that is as wide as 10 kilometers. And to see this event horizon, to see the shadows of the black hole, as it's been called, we had to do something incredible. We had to connect the telescope all over the surface of the Earth, from Europe to South America. From soon we're going to have some of the observation now I've taken from Greenland all the way to the South Pole. and together they've been synchronized to the millisecond to capture this, these two black holes and more. And what we have is something incredible. The first images of the black holes. The precision is outstanding. It's been compared to seeing a donut or a bagel on the surface of the moon with your naked eye. That is the kind of precision, because Sagittarius A star is 26,000 light years away. M87 is bigger, obviously, but it is 1,000 times further. So it's incredible that we can do that. And this observation has been incredible in helping us test the most cutting edge of our understanding of both black hole astrophysics, but also general relativity, which is, we know that are amazing, but it's science. We always need to test again and again and again. I did tease you that there was going to be a connection between space and cocktails, and this is my favorite connection. Radio observation we're able to discover. We're still in the neighborhood of Sagittarius A star. This cloud that you see on the side is called Sagittarius B2. It's a massive cloud of hydrogen near the center of the Milky Way. And it has a lot of interesting molecules that have been discovered thanks to radio waves, because as the molecules vibrate and rotate, they interact and they can emit radio waves, and we can capture those signals, the signature, with our radio telescope. And one of the most interesting things that is in this cloud is ethyl formate, which you probably might think, never heard of it. But I bet you have either smelled it or tasted it, because ethyl formate is responsible for the smell of rum, and it is responsible for about half the smell of raspberries. And it's so much fun making cocktails with raspberry and rum, and just like you see, you are tasting a little bit of a cosmic cloud. The idea is why are these molecules and many others found in here on Earth in plenty of plants, but also into cosmic clouds, because they are this building block of amino acids and proteins. So they are common, they are found everywhere. At least that is the assumption if we consider that life should be possible everywhere. We keep finding these precursors to amino acid in comets, in meteorite, in asteroids, and in these large molecular clouds. We don't know if they always lead to life. We don't know if there is something special, but it is really interesting to think that thanks to radio waves, we know all these very peculiar molecules in gas clouds that is 26,000 light years away. And yes, it's unfortunately I need to burst the bubble. The cloud itself doesn't smell of rum and taste like raspberry. But if we were also a cloud, a giant micro cloud like nebula is just too diffuse for us to be able to smell, even if we were in there. But let's assume if we could bottle it up and condense it, what could we smell? Probably almonds, because the most odorous, the most smelly components of this cloud is actually a cyanide. So wouldn't suggest you try it, but maybe that is the smell, the real smell of this cloud, if we could condense it. Another thing that it's exciting for the next few years is how we can use radio waves actively, not just passively observing the universe. We can create radar images of the moon, of asteroids, Potentially, we've used it on Venus, but not for imaging. I will discuss that in a second. Potentially, with radar, we could get all the way to create images of the moon of Saturn. That is quite a far distance away. And it's just by sending radio waves out and just be ready for when the radio waves come back. And something really exciting, as you can see here, this is a high precision moon observation. And with regard to the moon, we can actually see below the surface. Not like 20 kilometers, no, just a few meters. But it's very exciting because we can look at the areas where the astronauts are expected to come back for the next moon landing in the next few years and see if there are maybe ice deposit or something interesting, or if it's stable enough or it's just loose soil, so that we can actually help astronauts when they will go back to the moon. But also we can use it for planetary protection. I'm sure that you're all aware of asteroid 2024 YR4. We know that it's not going to hit us. It still has a small chance to hit the moon, which would be very interesting if you ask me, because we would be definitely see a new crater on the moon. That would be quite exciting. But imagine that if the risk to Earth was still quite serious, we could use radar images to better characterize the asteroid, to better track the asteroid as well. We could get the precision of the orbit down to 10 centimeters, which would be amazing. Is the fact that to do this kind of radar, you need to be very much on the ball, and it takes time, and we don't have that many systems around the world that can do that. But a really cool things that has been done with the Green Bank telescope, that have a small radar system, is to measure the rotation of Venus, because Venus has a very slow day. It's equivalent to 243 Earth days. And to measure it very precisely, they had to shine some radio waves and just wait for Venus to rotate and the radio waves to come back to us, like in a disco ball. And with that, they measure the day with really, really high precision. Really cool, really pragmatic way to use radio waves to discover something about the solar system. There's also the possibility of finding things that are completely absurd, if you ask me. This came out in January 2024. There's this thing called low surface brightness galaxies. They're galaxies that are very large, but have very few stars. They think that there is, maybe they are, it was caused by interaction, or they don't have enough dark matter to keep them together. And what happened is that they are very spread out and they look very diffuse. And there's this team that was looking at some low surface brightness galaxy, and they accidentally pointed at an area of the sky that should have no galaxy. But they had found a signal. So what they're measuring was hydrogen gas, and they do measure hydrogen gas in this low surface brightness galaxy. But they found this signal, and it was a real signal, but there was no galaxy there. And they got some time on the Hubble telescope to look at the area, and there are no stars. But they kept looking at it, there is a massive cloud of hydrogen as big as the Milky Way with no stars. And so there is a galaxy with no stars. And to me, it's like galaxies is the topic of my PhD. Is like galaxies should have stars. That is one of the fundamental requirements for a galaxy. But what do you call a cloud of hydrogen 100,000 light years across, if not a galaxy? And given that it was found by accident, it means this probably is not the only one. There's probably a lot more out there. We just need to go and be lucky and find them. We move to the next wavelength along, and it's microwaves. And behind we have the most famous of the microwave images, the cosmic microwave background. Microwaves is a lot of the application of microwaves are very close to radio waves, and some of them are very close to infrared light, so it sits in this weird in between. But the fact that the proof that you're looking at here is the proof that the universe started in Big Bang, and that the universe is a large scale, all the same, everywhere, in every direction. It requires the microwave are their own wavelength. What we see here is a thermal map of the universe as it was just 400,000 years after Big Bang, around 380,000 years. And this map tells us something fundamental. The difference in this temperature map, there's very small. The deepest red and the bluest blue are just 1/10,000 of a degree, so something tiny. The universe is mostly the same everywhere. But those differences pretty much planted the seed for where the galaxies and galaxy cluster were going to fall into. Those tiny differences ended up shaping the evolution of the universe over the next 13.8 billion years. And so it's something that is such a tiny difference at that time. It's has changed the universe, and it is probably one of the most important images ever taken in astronomy. But it's not. Microwaves is not just that. We can also study the birth of planets, because thanks to millimeter and submillimeter waves, we can go and look for the cool gas and dust peering further than what infrared light would allow us. And very useful, as you can see here on the side, on very, very young star systems that are literally just forming planets. And here I want to mention this star system because potentially we are looking at the first case of a co-orbital planet. So the star is there in the middle, is very fussy because it has a lot of gas around. We can see that something has clear quite a wide orbit. That must be the dark donut there in the middle. That is a planet has taken a lot of gas and material away, and we can see that in the biggest rounded thing in the solid circle. But on the same orbit, that is the ellipse, in the dashed line, there is a second object that also look quite dense. So it could be the first case of a co-orbital planet. And it might not be stable. It might be that in a few million years, it's kicked out, it's thrown towards the star, it's absorbed by the larger planet. But the fact that there is forming is telling us that the universe and planetary formation might be even more weird and more complicated than we expected. More on that when we get to infrared. And microwave also help us at the end of stars. So here is a wonderful, gorgeous picture of the Crab Nebula. We're gonna re-encounter a Crab Nebula later, but here in green and red, we're looking at the cooler gas, the gas that had been left over from the supernova that created a crab. Sorry, not the nebula, the crab pulsar. So we're looking at the coolest part of the gas, and that allows us to understand how this supernova happens. There is a lot that we don't know about the end process of stars, and given that the coolest gas has escaped before the supernova, it's very important to study it because we might learn what happened just before the supernova, something that remains very much mysterious. Infrared light, we've been spoiled by the images of JWST, like this glorious one from the Carina Nebula. And it's one thing that JWST allows is to see through gas clouds. In general, in infrared allows is to see through glass cloud. and we can see where the stars are born. We can see where the moments of star formation are happening. And I mentioned that there's still so much we don't know about how stars die. We also don't really know much about how they're born. There's a lot that we don't know about stars. And this kind of observation are helping so much in understanding how stars come to be and the first moments after, actually both before when there's just still a protostar to when a star is truly born, and it will help us understand why the solar system is the way it is. I told you the galaxies are my bread and butter, and probably this is for me like an image that I could stare at forever and ever. There's the full image of this JWST deep field had 45,000 galaxies. Every dot of light, apart that six pointed flare that is a star, everything else, it's a galaxy. Hundreds of them, when this picture was released, and never seen by human before. Some of them, some of the reddest dots are some of the most distant galaxy known. And the fact that we can do that, and this is a single image, a series of observations, but in a single image. The fact that we can see that and think there's so much more, it's incredible what we are capable to do with a telescope such as JWST. But another fun thing is this one. That is the Perseus cluster, and you are seeing there a observation from Hubble. And if I click, you should start seeing observation from the Spitzer infrared telescope, which was the predecessor of JWST. You can see these big waves of gas that go around. You can see it in the Hubble image. You can see it much better in infrared. And those are caused by the supermassive black holes at the center of this galaxy, because it is rotating with a period of 9.6 million years. And because it's creating repeating ripples, it is creating a harmonic, which is a musical note in physics. And it is a specific musical note. It's a B flat, 57 octave below middle C. Isn't that incredible? There is a black hole out there that is responsible for the deepest musical note in the universe. And it's just because it's rotating in a very interesting way. Potentially, it's between 2 and 6 billion times the mass of the sun, so maybe not as big as the one in M87. But why is it rotating in this pattern? Potentially as a second black hole orbiting, and it's created a sort of spinning top situation. So it has gas and is releasing this gas black holes are very, very messy eaters. So they try to gobble up, but half of what they eat, probably even more, is just spew out into the intergalactic space. So this is what's happening. It's throwing some of this gas out and creating this pattern. There is technically a black hole that has gone momentarily to a lower note, but it's a little bit tone deaf. We think that maybe is going to it's the same situation with a binary supermassive black holes, and that black holes is going to merge with its companion, because it started as something that was closer to 58 octaves below middle C, and now it is at 54. So things change. Instead, the one in the Perseus cluster, it's keeping its rhythm. Whatever is going on at the center of that massive galaxy, it's staying like this, and it's been staying like this for many, many millions of years. And I did mention that there is a lot that we don't understand also in planetary formation, and I don't think there is a better example than these things called the jumbos. They're called Jupiter mass binary objects, and they shouldn't exist. They as simple as I can tell you, they should not exist because we have this nice, neat classification. Things up to 13 times the mass of Jupiter, that's a planet. Things, and they form like a planet, so they form from little pebbles or little asteroid, they grow, get some gas, they grow, and they become a planet. And things up to, from massive stars to up to 13 times the mass of Jupiter, they form like stars. So a cloud collapses, and the smallest one becomes brown dwarf, which are very cold, and they are could be similar to planets. They have weather, atmospheres, aurora as well, but they form like stars. And we think there is a net difference. Some form like planets and some form like stars. And then astronomers were looking at the Orion Nebula, and they found this kind of things, jumbos. They're things that maybe are 3 times the mass of Jupiter. One potentially is the mass of Saturn, but they are in binary pairs. You see, if they're found something the mass of Jupiter just floating freely, they might say, oh, this formed like a planet in a star system, has been kicked out, and it's there. But these are in pairs. You cannot, so there's no situation in which you can kick 2 planets out of a star system and they just stick together. And you can see there are multiple of them. It's not just one example. So the best explanation is there are objects that have the size of planets, but they absolutely form like stars. So that brings the question of like, is there really a division of something forming like a planet and forming like a star? Could our Jupiter form like a star, but we classify it as a planet? We don't know, and it's amazing. We don't know. We didn't know that there were these objects until we accidentally stumble upon them. It's amazing. We couldn't have done it without infrared light and JWST. But let's move beyond the visible in the other direction, ultraviolet. So ultraviolet doesn't get as many fancy mission because a lot of things that we do in ultraviolet, other wavelengths sort of do. Like for example, ultraviolet here you can see Andromeda. It's very good to find young stars. But also using infrared to find the nice stellar nursery is very useful to find young stars, different wavelengths and different objects, but the same principle coming out. But in general, those young stars are UV polarized. So by using ultraviolet, we can really understand something important about galaxies. And NASA is now planning a specific ultraviolet mission. It's the first one in decades to be launched in the 2030s to just help understand how usually the local galaxy are changing because of the young stars, and also will help us understand what's happening to the Milky Way in the same way. Understanding the young stars and their effect on a galaxy is crucial if we want to understand how galaxies evolve. And we need to understand how galaxies evolve here in the more local universe if we want to understand how they evolved over the ages of the universe. But mostly ultraviolet light is used to study the sun, because thanks to ultraviolet we can see where the sun is at its most active, the spots, the flares, the coronal mass ejection, everything that we want to know about the sun is best studied in ultraviolet, and that allows us to keep safe because space weather is a serious concern, and space weather is dictated more or less by the activity in the sun. We are possibly now just out of the solar maximum, or we're just coming out of the solar maximum, so it's the most active time for the sun, and this is why it's very important to keep an eye on it. But another thing that is happening in the solar system that it's only possible to study in ultraviolet is a lot of world have ultraviolet aurora, and it's really cool. It's not some of Earth are that, but that the picture there is Mars that has ultraviolet aurora, even though it hasn't got a magnetic field. It's just the impact of the solar wind on the sun-facing side of Mars. But comets have ultraviolet aurora. Jupiter and Saturn, Venus as well has ultraviolet aurora. It's so spread out in the solar system, and it is amazing that this is happening, and we wouldn't know about this event, even though aurora on Earth, northern lights have been known since antiquity. We wouldn't know that other planets have them in different way if we didn't have ultraviolet light to see the universe. Next is X-rays. So X-rays were bringing up the real power in the universe. Here you're seeing the Whirlpool galaxies, a gorgeous merger, and pretty much everything that is bright purple, you're looking at either a binary pair that has a neutron star and very magnetic neutron star, or you're looking at a black hole. Either at the center of the two galaxies, or the one of the galaxies are actually supermassive black holes from even more distant galaxies. This is how we use X-rays, studying black holes, studying extreme objects, but also something quite close to home. So to the best of our ability, the best map of X-ray sky has been done by eRosita, and there are 900,000 unique X-ray sources in the sky. Remember, JWST, one single image was 45,000. This is the whole sky. It's very difficult to measure both X-rays and, as we're going to see, gamma rays. So those sources is just the best we can. Those are the brightest, the most powerful. Most of them are the supermassive black holes in other galaxies, but there are like 180,000. There are X-rays emitting stars from the Milky Way. Stars emit across the spectrum, as we will see. And one of them is our sun emits, is not like a massive emitter of X-rays, but the solar corona, the atmosphere of the sun. This is my picture from last year eclipse in Mexico. The atmosphere, the fuzzy atmosphere of the sun is so hot that it emits in X-rays. It's in the millions of degrees, while the surface of the sun is 6,000 degree, around 6,000 degrees. And that is a big mystery. How can something outside be hotter than what's underneath? And we think we're getting there thanks to Parker Solar Probe and the European Space Agency Solar Orbiter. We think we're getting a good understanding of the magnetic field through the solar corona, which is the atmosphere of the sun, and how these magnetic fields changes, release a lot of energy and heats up the atmosphere to millions of degrees. But it's something that it's only possible to study. Either we study during the eclipse, so we get those kind of, that is visible light that is influenced by the corona, or the other way is just having X-ray observation of the corona continuously in space, and that's what several observatory and spacecrafts do, and this is why it's important to study the sun also in X-ray, not just ultraviolet. And as mentioned, there are 12,000 left of those 900,000. There are neutron stars, such as the one, the Crab Pulsar, and they have great magnetic field, and this can accelerate particle, and by accelerating these particles, they produce X-rays. There's also X-rays from intergalactic gas, the same gas that we might find like around the Perseus cluster that created that beautiful note. Some of those gas around galaxies can reach millions of degrees simply by the effect of supermassive black holes throwing out stuff into space. And that is almost the limit of how hot something can get until you get to the gamma rays, and that is the limit. So this is the universe, this is the sky in gamma rays as best as we can see, and we have 7,000 known sources. Again, one image from JWST, 45,000 galaxies. All X-ray sky is 900,000. This is only 7,000 known sources. It's mostly because it's so difficult to measure and in a way trap the gamma ray photons. Are too energetic. But there are some events that are so bright that it doesn't matter that it's very difficult to capture. They outshine everything else in gamma rays. And those are the gamma ray bursts. There are two types, which one I call the reason for your appetite, because short gamma ray bursts are created when two neutron stars collide and merge, and they are less than 2 seconds long. And in those collisions, a lot of the heavy elements that we use here on Earth are produced. There's gold, platinum, and include iodine, which is the regulator of our thyroid, so our appetites. And so I always find that stars not only had to die in supernova to make most of us, the oxygen and the carbon and the iron in our blood, but you also need to have their corpses needs to smash into each other to have regular metabolism. Those events are crucial. But probably the most interesting one is the long gamma ray bursts. They can last several minutes. I think the longest been hours. And I want to show you this. This is the most powerful ever recorded. And you should be seeing here. So that is just gamma rays of observation, and suddenly you see something that outshines everything else. And that is sped up. It was caused by a supernova, massive star going supernova 2 billion light years away. And the energy of the light from that gamma ray burst. So we were the supernova created a very collimated ray of light, almost not exactly like a laser, but imagine a very concentrated beam of gamma rays, and Earth was right in the path. And even though it was 2 billion light years away, the hit of this gamma ray in the atmosphere, it generated ions. It broke molecules and atoms apart, and those ions were electrically charged, and it started moving toward the atmosphere so much that the entire atmosphere of our planet reverberated for 8 hours. And I think it's both so fascinating but also terrifying that something 2 billion light years away in another galaxy somehow can affect our planet's atmosphere and making it shake for 8 hours. And we wouldn't know if we didn't study the universe in gamma rays. So this is the tasting menu, as I said, of talk. I see that there are so many different application of astronomy beyond the visible light. But I will have to tell you that in the 60s, when the technology from radio waves, from infrared, started to be developed, astronomers were actually not interested in this. They didn't think there was any value in seeing beyond the visible. They thought that everything that we can see is very much will provide all the information. But clearly, as you've just heard, that is not the case. The last 7 decades have completely changed our understanding of the universe, and it was only possible thanks to the technological breakthrough that allowed to go for humans to go beyond our senses. And even light is not the end. We are truly at the beginning of a new revolution in astronomy. We had over the last 10 years, the detection of gravitational waves. We had detection of neutrino from space for a few decades now, but we've been able to track those some of those neutrino back to their sources. So we are starting to study the universe beyond with more than just light, with gravitational waves and neutrino. It is going to be a very exciting time for astronomy, and we should feel very, very lucky that we are right at the beginning to see where it's going. And with that, thank you very much. And I didn't update the discount code, sorry, but if you want to check out my book, that is the QR code. Thank you.
Thank you very much for this evening's presentation. So if you could just stop sharing your screen for a second, we will turn gallery view. So again, thank you very much, Alfredo, for this evening's talk. Now starts the questions portion of the evening. So people, please feel free to turn your videos back on if you want to start asking questions and getting involved. Hands up, please, as per normal on questions. Or have we been absolutely stumped by this evening? No questions whatsoever.
Was it too much? Have I just gave you too much information and you're just like, oh God.
Was it too much information? I mean, I personally. Sorry? Yes, no, waving.
I'm counting.
Counting with his finger and waving about, not a problem. So I'm always fascinated when statements like, you know, this is the hottest element in the universe, and it always boggles me and blows my mind a little bit that statement can be so boldly claimed. I much prefer the so far clause sort of in there. This is the hottest substance so far that we've discovered. But I'm stumped a little bit to see what else could actually be hotter.
It's
we had sorry, Alfredo.
Yeah.
You were going.
I was going to make a comment. Is just like you see, when it comes to temperature, and Paul, we're gonna get to your question immediately. There are some assumption of just we know that there is a lower limit, absolute zero, because things cannot move anymore at absolute zero. But there is this idea of at some point physics break, and we can discuss it is a true, our physics doesn't work anymore, but it could be physics beyond, or no, nothing breaks just like nothing works just like at absolute zero. It is a question for the theoretician to answer, but I think at the moment is very much, as far as we can tell so far, the hot, like this is probably how hot we can get a real gas between galaxies, and in the few tens of millions of degrees. There shouldn't be any hotter because of. So the problem is they get so hot and they're so far apart, these atoms, that they cannot radiate out, and that's how they get stuck being so hot. But I think higher than that, you start having fusion inside the atoms, and it's not happening because we can detect the species of the atoms. So one for the theoretician. Paul, would you like to ask a question?
Yes, please. Thank you very much for a very interesting talk, Alfredo. Going back to your starless galaxy, this cloud of hydrogen gas. Do you have any other information on it? Is it rotating? Does it seem to have
yes.
a center, etc.?
Yes. Not exactly a center, but to measure rotation, I'm assuming most of you are familiar with the concept of redshift.
Yes.
Yeah.
Yes. So quickly is if things is very similar to a Doppler. Actually, that is in this case it's a real Doppler shift, not the galactic redshift of things moving away. Is so like in the Doppler effect, an ambulance siren coming towards you as a higher pitch, then going away from you as a lower pitch, is the same with light. So to study the rotation of objects, usually galaxies, in astronomy, we can look if one side is slightly redder and one side is slightly bluer. They can see that that is the case. And in general, they are saying that maybe there are some stars, but they cannot, even with Hubble, they cannot detect them. It's and there's not exactly there must be a center if it's rotating because it's rotating around an axis, but there's nothing that it makes an obvious galactic core to say that. So if you're asking for if there is a center, there is a point in which this cloud is rotating, yes, it has at least one rotational axis, but it gets very complicated to study the three-dimensional motion of a place that you only have gas and you cannot see stars. But is there a center in the, as we intend with a galactic center, like a nice spiral galaxy with a nice bulge or a nice bar, or a nice elliptical galaxy that has a clear overdensity in the middle? That is not it doesn't look like so. They have this was presented to give you more information. This was presented at the American Astronomical Society meeting in January 2024. If I remember correctly, it came out on the 11th of January. It's one of those kind of things that is stuck in my mind because I had to search it multiple times for the book because I continue to think that it's just absurd to have a galaxy with no stars, but it's very interesting. And yes, so it rotates, is as wide as the Milky Way, is extremely massive. They estimated that it could have, it's very difficult, a lot of the mass estimation for galaxies are based on the luminosity, and we say, okay, you have this brightness, you should have X amount of stars, and so you should have this mass. And then we multiply that by 6 and say, okay, that is your real mass with the dark matter, and then we can do better estimation if we find global cluster around the galaxy or if they're in a system, etc. For this one, it's very complicated. You don't have the stars. So they assume roughly a sort of pancake shape of gas and say, okay, if you have a big gas cloud, how much is going to be? And it's still going to be quite a massive galaxy, even though no stars.
So just a quick
Yeah.
follow-up query on that. I presume, and it might be a wrong presumption, that there isn't enough information as yet or enough observations to indicate that that gas cloud is contracting, is collapsing under its own mass?
It doesn't look. This is my own speculation, but it's unlikely that it is doing that. If it was like a gas cloud that big, like you would in this is how galaxy might have started. You should have a pocket of that gas collapsing and forming stars, forming group of stars, but we don't see that. Their general idea is the fact that the whole system doesn't have maybe at something, or maybe the gas was too hot, so they stayed quite spread out, and the dark matter content in the galaxy is anomalous, so that it didn't push the gas to collapse into something smaller and from there creating stars. So I am pretty sure that is the correct answer, but we can go and look it up on the paper and the statement that they put out. But I would assume that if there's no star or no visible stars in this galaxy, it's because it is not collapsing. It's just a stable, extremely large gas cloud.
Can I just add one more thought?
Go for it. I'm sure that Chris will forgive you.
Okay. And that
I won't.
is there a chance then that this gas cloud is really primordial Big Bang material?
Uh, not probably yes. It would be very interesting, and maybe that's what they're doing. They're planning to do follow-ups on this to try and understand if it would be interesting to see if they could find any kind of other elements. Because if there are no stars, if there not been any stars formed in this, they should be quite pristine. There is this, you see, we have this idea that we need to find most pristine original things in the from the Big Bang only in places that have been uncontaminated. That cloud would be fantastic. That would be a fantastic example. But it's certainly possible that even by studying things that are closer to Earth, the large magellanic clouds are quite metal poor, they're quite primitive, not as primitive as that cloud might be, or something that has been untouched since the Big Bang. But there might be stars, there are small stars that form very quickly after the Big Bang that have very little pollutants. Yes, we're hoping to find the biggest stars that ever formed, the one in population 3 stars, the one that were almost pure hydrogen, almost pure hydrogen with a little bit of helium. But there also might be smaller stars like that, and they might exist. Even in the Milky Way might exist stars like that. It's just that very difficult to find because you have a lot of other stars that are a lot more complicated, and it's just things get difficult to find those special ones. But you're absolutely right. It could be that it's a pristine cloud of hydrogen from the Big Bang. We follow up studies, and they're very, very keen in trying to follow up on that because it's just so weird. They weren't expecting something like that to exist.
Thank you, Alfredo.
You're welcome, Paul. Chris.
Hi there. Thank you for such a fascinating talk, Alfredo.
You're welcome.
Really looking forward to that. The as a bassist, the one that caught me out was the lowest notes, 57 octaves. I like to think that my bass gets pretty low down. I can get down into the 0 octave. But 57 below middle C, I've just been trying to do the calculations in my head of what the hertz would be on that. And even I'm struggling. What?
It's the reverse of 9.6 million years.
Yeah, a long,
so
long
it's
time.
1
then.
over 9.6 million.
1 over 9.6 million.
So let's make it round and go 1 over 10 million. So it's 10 millionth. 10 millionth. Oh no, God. Yes, is 0.00000000001 hertz, something like that. But
Yeah.
yes, but this is why it's so fascinating. Is the fact literally just from among those waves there is a sort of tsunami of gas. There's a little bump, probably from an initial interaction, and that is 200,000 light years across. That is 2 Milky Ways across. And that was the beginning, the focus, because like, oh, something happened there. There must have been some interaction in this black hole. But then they started just looking that it was this repeating waves every 9.6 million years and realized, wait a minute, if it's just so periodical, that's a harmonic. That's a note. It's absurdly low, but it is a note.
Very.
It is fantastic. I do love this connection between something that is tangible, like music and harmonics, to something that is absolutely not tangible, like a supermassive black hole. Or I love making cocktails, so the gas cloud and the rum. It's I really want to communicate that for as much as it's incredible that we can picture these amazing things in the cosmos, a lot of aspects of it that are pragmatic because physics is all the same. It works good here and it works good out there, as far as we can understand it.
Mm. That has actually made me also want to go and get a really nice big glass of Kraken as well.
Well, that is a good choice. I would suggest you make a little raspberry syrup, very easy to make, and a little bit of lime, and you have yourself a very nice cosmic cocktail.
Astrophysics and cocktails, good
Astrophysics
combination.
and cocktails, yes.
Thank you.
Very welcome.
Excellent. Do we have any questions that got rattled out of people's ears during that point? There's nothing in the room. Anything online? Anything fall from behind the back of the sofa that you'd like to ask? Well, in which case, I just want to give you your last opportunity, Alfredo. If there's absolutely anything else, any words of wisdom before we thank you for your time this evening. Now's the time to impart your wisdom.
No, I'll just say thank you very much. We discussed the planetary parade. I've seen 3. I hate Mercury. I never get to see Mercury. I hope that you have better luck if you're trying to see the planets over the next week.
Well, thank you very much for our taster. So thank you very much for our small tapas. And it leaves me to ask everyone from the Mexican and Swinton Astronomical Society to give you a very, very warm thank you.
Thank you. Have a lovely rest of your evening.